If I were to get pushed into a pool, I would sink. But why do I sink, and why does a huge cruise ship float?
This can be explained by Archimedes' principle, which has to do with buoyancy. Most people have heard of this force that allows objects to float in water, but right now we are going to jump into some of the science behind it.
Archimedes was a Greek mathematician and inventor. He discovered this concept of buoyancy in Syracuse, Sicily around 3000 BC. Legend has it that he had a striking revelation in the bathtub and ran naked to the king to share his news. Luckily for you, we will not be reenacting this revelation, but we will be looking at the formula for buoyancy and Archimedes' principle here. Buoyant force is the net upward force on any object in any fluid. If the force of gravity on the object is greater than the buoyant force, then the object will sink. If the buoyant force is greater than the force of gravity on the object, then the object will float. But where is that buoyant force coming from, and how can we manipulate it to our advantage? This is where Archimedes' principle comes into play. Archimedes' principle states that any object, fully or partially submerged in a fluid, is pushed upward by a buoyant force equal to the weight of the fluid displaced by the object. This is represented by the equation here. The weight of an object is equal to the force of gravity on an object, so we will look at the force of gravity on the displaced fluid. The force of gravity on an object is equal to the mass of the object times the gravitational constant g. G is a constant roughly equivalent to 9.8, and it does not change. So now, all we need to figure out is the mass of the displaced fluid. The mass of a fluid can be calculated by multiplying the density of the fluid by the volume of the fluid being measured. We know the density of a fluid, and the volume of the fluid we want to measure is the volume of the fluid being displaced, which is the volume of the object. So plugging everything back in, our final formula is the buoyant force equals the density of the fluid times the volume of the object times the gravitational constant g. And now that we have all the pieces of the equation for buoyant force, we can see that buoyant force is proportional to the density of the fluid and the volume of water displaced. This means that as the density of the fluid and/or the volume of water displaced increases, so does the buoyant force. So let's look at some of the ways we can affect buoyant force in the real world. We can take this lump of clay here, and when we drop it, it sinks to the bottom. The clay is very heavy and does not displace a large amount of water, so the buoyant force is smaller than the force of gravity. However, when I take this exact same piece of clay and change only the shape, it floats. This is because now the volume of water being displaced is much greater, which leads to the buoyant force being greater than the force of gravity. This is the reason that huge boats float as well. They are very heavy, but they displace a lot of water, so the buoyant force balances it out. We can also examine how density of a fluid affects buoyant force. The water here has a density of 997 kilograms per meters cubed, but if we were to place our object in a much denser fluid, like honey, which has a density of 1,420 kilograms per meters cubed, then a greater buoyant force will be exhibited on the object, and so the object will float in honey, but not in water.
These examples are just a few of the many ways that we can affect buoyancy. But everyone can wield this incredibly useful force with just a little bit of science. So go get creative and try not to fall in.